Swayam Prabha. Digital India. Educated India.
Hello everyone, I am Modal, Professor in the Department of Mechanical Engineering at IIT Delhi. This is the first lecture of my course on experimental model analysis. In this lecture today, I will introduce briefly the experimental model analysis and present the relevant background of experimental model analysis. We will try to answer some relevant questions like what is experimental model analysis, what is vibration, why vibration occurs, what are the detrimental effects of vibration, that is why vibration needs to be reduced, and finally we will try to present some motivations for experimental model analysis. So before we proceed to answer these questions, let me first present a brief outline of this course. So the course would start with introduction and background, then we will try to lay a theoretical basis for experimental model analysis. Understanding theoretical basis requires understanding of theoretical models or mathematical models of vibratory systems. And therefore, the next topic would be that we will try to look at what are lump parameter models of vibratory systems and how to develop governing equations of motion for these models. Then we will look at analytical model analysis of single degree of freedom systems, in which we will cover the free and force vibrations of single degree of freedom undamped and damped systems. Then we will look at analytical model analysis of undamped multi degree of freedom systems, and then analytical model analysis of damped multi degree of freedom systems. In this all topics, we will also develop some important concepts like frequency response functions, modal space, impulse response function, and so on, which are relevant to understanding the experimental model analysis. Then we will try to see what are the important characteristics of frequency response functions and how they can be graphically presented. Then we will look at signal processing issues or signal processing for model analysis, and we will try to understand that how digital signal processing can be used to obtain the frequency domain representation of say response signal and the force signals, and some other pitfalls of the digital signal processing like aliasing, leakage, quantitation error also we will discuss. Then we will look at how FRFs can be measured on using impact hammer. Then we will look at FRF measurement using a vibration shaker or exciter, and then how the FRFs are then curve fitted to obtain modal parameters. So we will look at modal parameter estimation using frequency response functions and impulse response functions. Depending upon the available time at the end, we will also try to briefly look at phase resonance testing, operational model analysis, and some applications of experimental model analysis. So this is broadly the the topics we are going to cover in this course. So let us now address the first question, that is, what is experimental model analysis? What is experimental model analysis? In order to understand what is experimental model analysis, I think we need to first understand what are natural modes of vibration. What are natural modes of vibration? So, the natural modes of vibration of a system are the principal or the distinct ways a system can vibrate naturally with harmonic motion, right. So, the natural modes are the distinct ways by which system can vibrate harmonically. So, the system can vibrate naturally or freely, which is not a natural mode of vibration, right. So, free vibration which is not a natural mode is possible, right, but there are distinct ways in which a system can vibrate freely with harmonic motion. To take an example, let us take example of a simple pendulum, right. The simple pendulum, if we disturb this pendulum, let us say keeping the amplitude of motion small, say like this, then if it is displaced, then it is going to oscillate. So, this is the, it will go to the other extreme like this, and then it will keep on oscillating like this. So, if theta is the amplitude of motion, right, and if theta is small, then it can be shown that this theta as a function of time can be written as some theta naught times say cos omega and t, okay. And therefore, the description of the displacement of the pendulum can be described by a cosine function. If a different disturbance is given, it can also be described by a sine function or a combination of sine and cos function. But the important point is that the frequency of these motions is this, which is nothing but the coefficient of time t, and this frequency is same irrespective of way this pendulum is disturbed, keeping of course the amplitude small, and this frequency is called natural frequency. Simply because the pendulum once disturbed is no longer excited further. So, it means it is under free vibration, and the frequency in this state is the natural frequency of the system. Now, this pendulum requires only one coordinate theta to specify its displaced configuration, and therefore, this system is referred as a single degree of freedom system. And this is such a system, and any single degree of freedom system has only one natural frequency, right. Let us take another example. Let us take a system like this, in which we are connecting two identical pendulums, say by a spring like this. Okay, so there are two pendulums which are identical, and we are connecting it by a spring. Now, this system has 2 degrees of freedom, because the displaced configuration of the two pendulums at any point of time, right, it requires two coordinates theta 1 and theta 2 to be specified, so that the displaced configuration can be specified. So, this system has degree of freedom 2. Now, this system has two natural modes of vibration. One of the natural mode is this, in which the two pendulums are displaced by an equal amount, say if I call it say theta naught, theta naught. So, in this case this system vibrates with natural frequency omega n 1, right. So, it means when the pendulum system goes to the other extreme of the cycle, then they occupy a position like this, okay, they occupy a position like this. So, and they keep on oscillating like this. So, one of the important characteristics is that this motion, number one, it is harmonic motion, and its frequency is the frequency of that motion, of that natural motion, is that is nothing but omega in1, the natural frequency. And it is also seen that the two pendulums, they have a synchronous motion, right. So, their amplitudes, they are always in the same ratio at all times of time, and this is another important characteristic of natural mode of vibration, right. So, it means the two pendulums, the displacement of the two pendulums, they increase or decrease in the same proportion with time, and this description of the displacement of the two pendulums of in this particular, in this mode of vibration, or in fact any mode of vibration, is referred as the mode shape of that mode. So, it means we also have something called mode shape, this I can say mode shape 1, right. So, this mode shape 1 basically prescribes that how the displacement of the two masses of the pendulum are going to change, right, how they are related rather, right. And this is again a property of this mode. So, this is mode 1. So, let me just write here, this is mode 1. There is another mode, natural mode of vibration, which is possible for this system, is which is in which the two pendulums, they move in the opposite direction, they move out of, their motion is out of phase like this. So, if this is say theta naught, then this is, so maybe it's okay, this is theta naught here. So, therefore, what is going to happen? The motion of the two pendulums in this mode, it is out of phase. When one pendulum moves to the right, the other pendulum moves to the left, and when the other pendulum moves to the left, the other one moves to the right. And this particular motion again is associated with a frequency, and since it is the free vibration occurring in a specific mode, we call it natural frequency, right. And the associated displacement shape is called mode shape, and we call it, let us say, mode shape 2, and this mode is nothing but the second mode of vibration of this system, okay. So, therefore, we see that these are the two natural modes of this system, and there is no other way in which system can vibrate such that it has harmonic motion. There is no other way. For example, if we disturb the system keeping the amplitude of the first pendulum 0 and displace the other pendulum by some amount and relieve the system or release the system, then this system is, this vibration is also, will also be a free vibration, right. It is also a free vibration, but it is not in a particular mode, right. It is not either in the mode 1 or mode 2, and therefore, it is not a natural mode of vibration. In fact, the free vibration in this particular configuration or with this particular disturbance can be shown to be a linear combination of the motions in mode 1 and mode 2. So, therefore, the natural modes are the principal ways in which a system can vibrate naturally with harmonic motion, right. So, a general disturbance given to a system also produces natural vibration or produces free vibration of the system, right. However, that free vibration is not purely in any mode of vibration, it is not harmonic in nature, it is a combination of several natural motions or the natural motions in different modes, natural modes of the system. The natural modes therefore are associated with Natural modes are associated with natural frequencies, right. For each mode there is a natural frequency, then mode shapes. For each mode there is a corresponding mode shape, and in practical systems you see that there is also damping, and damping basically causes dissipation of energy, and therefore each mode is also associated with what is called as damping factor. So, this is something we will discuss in the lectures later. So, each mode is also associated with what is called as damping factor, which prescribes how the vibration decays in that mode. So, therefore, the natural modes are characterized by natural frequency, mode shapes and damping factors. So, the question is that is it important to know this characteristics of natural modes of a system? Yes, it is important, because the response of any system, right, the vibratory response of any system is determined by these natural modes. These natural modes affect the response of a vibratory system to a given set of forces, and hence it is important for us to know these natural modes, so that we can then figure out or determine that how the vibration response can be reduced. Therefore, identifying these characteristics is important. And now we come to our original question, that what is experimental modal analysis? So, experimental modal analysis is a procedure for experimentally identifying these characteristics of natural modes for a given system. So, experimental modal analysis, which we can just abbreviate as EMA, is a method of or procedure of identifying modal or dynamic characteristics, right. Modal or dynamic characteristics of a system, and these characteristics, natural frequencies, mode shapes and damping factors, they are also commonly referred as modal or dynamic characteristics, right. So, they are also referred as modal dynamic characteristics in short. So, experimental analysis is a method of is a procedure of identifying modal or dynamic characteristics of a system experimentally. So, later we will look at what is the motivation for identifying these characteristics, how do they help us, we will see later. Now, another important thing we need to note is that the natural modes are defined for a linear system. Natural modes, they are defined for a linear system, and therefore, one of the since modal analysis is related to identifying modal characteristics or characteristics of natural modes, it is clear that one of the important assumptions in modal analysis is that the system is linear. Okay. So, modal analysis, experimental analysis or modal analysis assumes the system to be linear. Okay. So, whatever system is being analyzed, it is assumed that that system is linear. And what is a linear system? A system is linear if it satisfies the principle of superposition, right. A system which satisfies the principle of superposition is a linear system. And what is principle of superposition? Let us represent a system by an input output model, right, in which we represent the system by a block, that is the system, and input of the system is represented by this arrow at the input, and output is represented by another arrow, right, which is the output. So, let us suppose that we apply on this system an input F1, let us say force F1 is applied, and let us say the response of the system is x1, right, and let us also say that if we apply input F2, let the response is x2, correct, and if I apply the force F1 plus F2, right, a combination of these two forces, and if the response is x, okay. So, the principle of superposition says that if x is equal to x1 plus x2, right. So, the output due to the combined forces, if that is equal to the algebraic sum of the output due to individual forces, if that is so, then the principle of superposition is satisfied and system is said to be linear, okay. So, that is the basic idea of a linear system. Now, in practice, many systems have some degree of non-linearity, and but the important thing is that many systems can be approximated as linear for small amplitudes of motion. To understand this, let me take the example of, let us say, a system with a non-linear stiffness, right. So, if I take the example of non-linear stiffness, a system with a non-linear stiffness, then what is mean by non-linear stiffness? That if we plot, let us say, if we apply the force on the system and record its displacement, right. So, let us say record its displacement x, and if we plot this, then the behavior may be something like this. So, we know that the relationship between the force and displacement is non-linear, and the stiffness is basically nothing but the first derivative of force with displacement, right, or which also we can roughly write as delta f by delta x. So, basically the stiffness of the system is the slope of this curve, force deflection curve at any particular value of x, and we can see from this figure that in the lower range the slope is different, and if we go up the displacement, the slope is different, right. You can see the slopes are different for different values of x. So, this system has a non-linear stiffness, but if the range of operation of the system, right, is such that the amplitudes encountered are small, the displacement of the system is small. So, let us say if the system is operating in this range, right, so it is operating in this range with this much displacement, then we see that the force deflection characteristics can be approximated by a straight line in this range, and we can treat the system as approximately linear, right. We can treat the system as linear, and therefore, the modal analysis principles can be applied for analysis of this system. So, therefore, we see that many systems in practice will have some degree of non-linearity. However, still in practice the modal analysis and experimental analysis is widely used because for small range of motions the systems, though maybe the nonlinear systems also behave more or less like linear systems, right. The developments in modal analysis, experimental modal analysis, were motivated by need to reduce vibration levels, higher dynamic response, and therefore one of the important goals of experimental modal analysis is reduction of vibration in systems and structures. So let us try to address some relevant background of this vibration, that what is vibration. What is vibration? So vibration is nothing but the oscillatory motion, and we are dealing with physical systems, and hence we can say that it is nothing but the oscillatory motion of a physical system, right. So vibration is nothing but the oscillatory motion right, of course, of a physical system. And when we say oscillatory motion, motion means basically the parameters like displacement, velocity, acceleration, these are the parameters which characterize the motion of a system, right. So therefore when we prescribe the displacement or velocity or acceleration or all of them as a function of time, then basically we are prescribing the vibration of a system, okay. So the oscillatory motion is prescribed in terms of the displacement as a function of time, velocity as a function of time. So, 1 dot over x represents velocity, 2 dots represent acceleration, okay, because velocity is the first derivative of x and acceleration is the second derivative of x. Therefore, we put 1 dot or 2 dot depending upon the number of times we are differentiating the displacement. So, the oscillatory motion can be described in this manner. But we should also remember that this is not the only kind of oscillations which occur in nature. For example, oscillations occur also in acoustic systems, right, oscillation of acoustic systems. So the sound is nothing but the acoustic oscillation. Any pressure fluctuation in any medium, typically the air, that is nothing but the fluctuation of air, and that changes with time. So that is oscillation of the air, and that is the oscillation of the acoustic pressure. We also have oscillations in electrical circuits, right, oscillations in electrical systems. For example, we have all studied RLC circuit. So if you give input voltage to the circuit which is oscillatory, then the current produced in the circuit is also oscillatory, right. And in fact, the supply we get in our households is an alternating current supply. So therefore, the voltage being delivered to the households is alternating in nature, and therefore the current it generates is also alternating. So there are oscillations. However, we are restricting ourselves to oscillations of a physical system described by displacement, velocity and acceleration, right, which we call as vibration. So the next obvious question is that why do vibration occur? Why do vibrations occur? Vibration occurs because of the dynamic forces, right. They occur because the dynamic forces, they act on the system. Let us again look at the input output model of a system. So let us say we have a force Fx on this, right, and if the force is static, which means that it stays constant with time. So this is nothing but a static force. Then the displacement it produces under the steady state, right, that is also constant with time. Okay. It is also constant with time. Of course, there may be some initial transient which we may ignore at the moment. So, there would be so displacement is constant with time. So, you have a static displacement, right, or static deformation. But let us take the case where this force is not static, right. The force we have is, let us say, varying with time, say something like this, like a cosine wave. Then we see that the displacement it produces also is going to vary with the time at the same frequency, and what we see is that because the force here is varying, the displacement x is also varying. So, it means the system goes away from its static position to some extreme, it returns back and goes to some other extreme on the other side, and this process repeats, and that is nothing but oscillation. So, you can see this is nothing but the oscillatory motion. And nothing but vibration. Okay. So, we understand that therefore, if the force is oscillatory, and such forces we refer as dynamic forces, right, dynamic forces which vary with time, they produce what is called as vibration, or we can also call it as dynamic response. The response is also dynamic. The dynamic forces need not be vary only in this manner like shown here, like cosine wave. No, they can be much more vary in a much more arbitrary and random manner, right. For example, the forces may be like this. So, that is also a dynamic force, and the vibration it would produce would also be would be quite irregular and varying in a quite random manner like this. So, depending upon the forces that are acting, the vibration or the produced will be depending on that, right. So, therefore, the vibration occurs because of dynamic forces. But what are the origins of the dynamic forces? What are the sources of dynamic forces in practice? So, what are the sources of dynamic forces? So, one of the important source is rotating unbalance force due to rotating unbalance. So, many machines they have rotating elements, right, like for example turbines, fans, compressors, centrifugal compressors, right, motors, generators. So, there are many machines which have rotating elements, okay. And these rotating elements they have generally their center of mass. We would ideally like that the center of mass of the rotating element is at its axis of rotation, but that is very difficult to satisfy, right, that is very difficult to achieve. So, if this is the let us say rotating element, right, on this shaft, and therefore, what has happened, let us say this is the center of mass. So, the center of mass may not be exactly at the axis of rotation. So, this distance is called eccentricity, right, and then what happens, this if the m is the mass, if m is the mass of this rotating element, then and if the angular velocity is omega, then m into E into omega square is the centrifugal force that it creates, right. And this force is a rotating force, and that is why you can see it is going to change direction. So, it means it has two components, this is one component and this is another component. So, let us say if the time t is equal to 0 coincides with this axis, then this angle is omega t, and therefore, this force will be m e omega square cos omega t, and this force will be m e omega square sin omega t. So, effectively what is going to happen? You have basically two forces acting on the whole system, because this force finally will be transferred, will be acting on the shaft carrying the rotating element, and shaft being supported in bearings, the force will be transferred to the bearings, right, in the form of reactions. So, and then the reaction, those bearings are mounted in the housing in the machine, so that forces will be transmitted to the housing of the machine, right. So, effectively what is going to happen, that machine is going to shake because of these forces. So, that is why and then in turn the whole machine and different elements of it will be set into vibration. So, therefore, rotating unbalance is a very common cause of vibrations in structures and machines. Another source is reciprocating unbalance. Right. So, many machines have reciprocating parts, for example, IC engines, right, they have a slider crank mechanism, and therefore, if I show here, this is the slider or the piston, and this is the connecting rod, and then we have this is the connecting rod, crank, and then the bearing, right, crankshaft. So, therefore, this is the piston which is reciprocating, and this connecting rod has a superposition of two kinds of motion, reciprocating motion because it is connected to piston, and on the other end is connecting to the crank, which is purely having a pure rotation. So, it is a combination of rotation and reciprocating motion. So, therefore, some mass of the connecting rod also can be considered to have reciprocating motion. So, what happens is because of this reciprocating mass, it is being continuously accelerated, right. So, the piston on the two extremes it has velocity 0, right, and then it has to reach from one end to other end. So, therefore, it has to be accelerated and again it has to be retarded. So, because of that the inertia forces are generated, and that basically then cause this causes the dynamic force and a dynamic couple, right. So, this inertia force due to reciprocating parts, it leads to a dynamic force acting on the frame supporting this mechanism, and a shaking couple which is a dynamic couple, right. So, it basically leads to dynamic force and dynamic couple. So, they vary with time and then going to cause the vibration of the whole that machine. So, wherever you have reciprocating parts, and if they are not completely balanced, then the unbalance, reciprocating unbalance will lead to these forces. Then we have operating forces, right. So, machines when they they are operating. So, because of the operation of the machine, depending upon the kind of machine, the forces may be generated, right. For example, in metal cutting, say metal cutting, say in a milling machine, right. So, when the milling cutter removes the material from the surface of a plate, let us suppose, then it applies cutting forces, right. And those forces generated in cutting, they act not only on the workpiece, but they also act on the milling cutter or the tool, right, cutting tool, and cutting tool is held in a tool post that is also subjected to those forces, and then the whole body of the machine is also subjected to the forces. And because these forces again are dynamic, they are not static forces, they vary with time, and therefore, the whole machine and different parts of it are subjected to these time varying dynamic forces which may lead to the vibration of the workpiece, the tool and the rest of the machine. So, that again is undesirable, right. The other example is, for example, the forces in forging, right. In a forging machine, the hammer applies a very huge impact force on the workpiece to produce the forge, and it is a very very high impact force, right. In a short time a very huge amount of force is applied, and that basically shakes the whole machine, the foundation on which the machine is installed, and therefore it causes the vibration. So therefore in other machines also, because of the operational forces, because of the operation, some forces might be generated which will cause vibration of the machine. There may be ambient forces, right. There may be ambient forces. For example, one of the ambient force is wind, right, wind loading. This is especially quite prominent in case of forces on civil engineering structures, like a tall building subjected to wind, right. So, wind blows and the velocity of the wind changes. So, because of that the load on the building because of the wind is basically changes with time, and therefore it basically causes a dynamic load on the building, and that may shake the building. And other example is earthquake, right. So, earthquake basically is relative motion between the different layers of the earth crust, and that relative motion is again transient in nature. It occurs for a short time, there is a sudden slip between different layers, right. So, there is a continuous activity under the earth, and because of that there is some relative movement that might takes place, right, and that basically is then acts like a transient ground motion, right, and all the structures which are there on the ground, they are subjected to that transverse transient motion, which basically is like a momentary big displacement of the foundation of different those structures, and which causes their vibration. So, that again therefore is dynamic in nature. Waves in sea, for example, is another source of ambient loading, which is basically relevant for ships, right. So, therefore, waves they impinge on the hull of a ship and they excite the hull, causing its vibration. Another ambient excitation could be acoustic, right. So, whenever there are sound waves, acoustic waves are basically the waves created in any medium. It could be like air or water or liquid or solid also. So, the waves created in this any of the medium are basically they travel, they propagate in different directions, and these are nothing but the acoustic waves, and therefore, especially the waves created in air, they can impinge or they do impinge on the structures with which they come into contact, and those structures in turn are subjected to the acoustic pressure, and because pressure is fluctuating, the load generated because of these waves on the structures are also fluctuating, and hence constitute dynamic forces on those structures. So, therefore, the sound also can sound or acoustic waves can also excite the structures. Then there could be also due to fluid flow, right, in pipes and ducts. So, many systems machines have fluid flowing in pipes and ducts, right. So, the turbulence in the flow, right, that creates forces on the walls of the pipe and duct. Because of the variation in the geometry may also lead to forces. So, all those effects may also cause excitation of the structure of the pipe, right, and vibrate it. Even if there is a flow of fluid, right, fluid flow past a body, right, or structure, that also may excite the structure. So, one example is that if we have, let us say, a pillar of a bridge, right, in a river, for example. So what happens? So there may be formation of eddies due to the flow, right. So this is the fluid flow at some velocity, and because of this there may be formation of eddies like this here. So these eddies which generate due to turbulence, due to the obstruction placed in the path of the flow, these eddies may excite the pillar, and then this pillar may vibrate in this direction. So this is often referred as self-excited vibration. So I think these are some of the sources or the origins for appearance of dynamic forces on machines and structures which excite the system. So now the question is that, is this vibration undesirable? Does it have any detrimental effect on the machines and structures? So let us try to look at that, how this vibration affects machines and structures. So let us look at what are its detrimental effects. So one of the most important effect of vibration is that it causes fatigue of the system which is undergoing vibration, right, fatigue. And how the vibration leads to fatigue? To understand this, let us take a simple example. Let us say we have a motor, electric motor mounted on a bracket, right, and bracket is fixed to the wall and it is supporting, and let us say the bracket is in the form of a in the form of a short cantilever, and we have this electric motor mounted on the bracket like this, right. And as we said before that rotating elements they will have some inherent unbalance left. So whatever efforts are made to balance the rotating part of that say the motor, still it would not be possible to completely balance it or to eliminate the unbalance completely, right. So therefore there would be some unbalance in the armature of the motor, and when the motor rotates, that a centrifugal force is generated which causes excitation, right, which leads to an excitation force in the both directions, right, in the vertical and the horizontal direction. And if I focus my attention on the force created in the vertical direction, which we can call as m e omega square say sin omega t, right. If omega is the speed of the motor, then this is the centrifugal force, this is the excitation force created on the system, right. And now what is going to happen? This force is going to vary like this with time, okay, and this bracket is therefore subjected to vibration. So this bracket is going to vibrate in this manner, right. If let us say this is the mean position of the bracket, right, then in the upward direction it goes to this extreme, right, and then in the downward direction it goes to this extreme like this, okay. And if we focus our attention on, let us say a fiber, let us say this is the neutral axis of this cantilever, and if we focus our attention on, let us say, this fiber which is at a certain distance from the neutral axis, right, and let us call this fiber as 1 2, right. So Therefore, this fiber when the bracket is moving up will take this position, right, and this fiber will be under compression, right. There would be a longitudinal compressive strain in the fiber, its length would reduce because it is above the neutral axis and the bracket is moving up. So, it is going to have a negative strain, and negative strain or compressive strain will lead to a compressive stress minus sigma. When the bracket moves to the lower side in the next cycle, in the next half of the cycle, then the position of the fiber will be somewhere here, and in this position the length of the fiber will increase, okay, from its length or unloaded length, right, unstretched length, and it would lead to a tensile strain and therefore a tensile stress. Therefore, if we now plot the, let us say, the stress in this fiber 2, right, 1 2 as a function of time, then we are likely to, we will basically, we are looking at this kind of picture, right, we are looking at this kind of picture. So, it means it has negative stress, then in the one half cycle, in the next half cycle it has positive stress, negative stress, positive stress. So, we can easily see that this fiber is subjected to alternating positive and negative stresses, and that is nothing but fatigue, right. So, that is nothing but the fatigue, because we know that the fatigue occurs if a any structure is loaded with a alternating load, right, or a varying load. So, any load which varies on the structure leads to variable displacement, variable stresses, variable strains, and therefore, the what is the ill effect of that? That the life of that structure or system, that would be less than the case if the load were static. So, the fatigue, therefore, it reduces the life. So, the vibration leads to fatigue and fatigue reduces the life, and therefore, that is one reason why vibrations are undesirable, because they would lead to systems and structures with lesser life. Another effect is that they lead to reduced life of bearings also, because finally what happens, the dynamic loads which are generated, they are finally transmitted to supporting surfaces. When we have rotating elements or rotating elements, we have some bearings, right. So, they will be subjected to higher levels of dynamic forces, and therefore, the life of those bearings also will reduce. Another detrimental effect is that it may lead to increase friction, wear and tear. So, often higher levels of vibration they hinder with the relative motion of different elements of a system, and which may lead to increased level of friction, right, and therefore, higher wear and higher tear of those elements. It also leads to reduced performance. It may also lead to reduced performance. For example, in measurement in instruments and measuring systems, if there are vibrations, then the accuracy of measurement is likely to reduce, and therefore, the performance of the system reduces. In machine tools, for example, which are meant for metal cutting or mass or production, so again vibration will lead to drop in the accuracy of machining. So, therefore, in general the vibration in systems and structures, it leads to reduced performance. Reduce ride comfort in passenger vehicles, right. So, another ill effect is that in passenger vehicles like say automobiles, railway or aeroplane, any passenger transportation system, right, transportation vehicle, you have if vibrations are there, the ride comfort will reduce, right. We do not want vibration beyond a certain limit, and if vibrations are higher, the ride comfort is sacrificed. The vibration also often leads to increased noise. Increased noise. So, one of the mechanisms of noise generation or sound generation is the vibration, right, vibration of surfaces, and therefore, if machines have vibration, they often lead to radiate a lot of noise, and that is something undesirable. So, these are basically the detrimental effects of vibration, but then are there any advantages of vibration in any cases? Is vibration desirable in any circumstances? Some applications of vibrations are so vibration phenomena is also used for some productive purpose. For example, in case of musical systems, in some musical systems vibrations are induced to generate music or sound, right, which is desirable. For example, in an acoustic guitar, the vibration of string is generated, the string is set into vibration to produce the sound, right. The vibration of string is transmitted via its supports to the box of the guitar, which in turn then vibrates and causes oscillations in the air inside the box, which leads to acoustic modes being excited of that box, which then in turn produces sound. So, therefore, here the vibration is intentionally induced to produce the certain music. Vibratory conveyors, right, is another application where a small amount of vibration is given to a conveyor to push forward the granular material kept on the conveyor. So, the vibration is used for transportation of granular material. Vibration exciter is another application. We will also study and use vibration exciter for modal testing. So, vibration exciter is used to intentionally subject an object or a product to vibration. So, one of the application of vibration exciter is in acceptance testing, where especially the electronic equipment, right, electronic PCB boards, etc., they need to be tested for their ability to sustain the harsh environments in which the machine, etc., in which they are to be installed are supposed to operate. And therefore, in advance in the laboratory, we subject those electronic equipment to certain levels of vibrations which they are supposed to encounter in practice, and test whether test their integrity and their ability to sustain the vibrations without sustaining any failure. So, therefore, that is one application. Other application is in the modal testing, where we would like to excite the structure with the intention of identifying the characteristics of its natural modes, right. So, that is another application. So, I think these are some of the applications of vibration. However, in most engineering systems, generally the vibration is undesirable, right. So, it is undesirable in most engineering systems. Most engineering systems vibrations is undesirable. Right, and it is desired that the vibration amplitude, right, is less than or equal to the permissible vibration levels. That is what is desired. And a permissible level of vibration is set based on the safety of the equipment in mind, the performance requirements in mind. So, those are the basically inputs which allow us to determine or fix the permissible vibration levels, right. And then it is desired that that in system or structure is designed such that the vibration levels it encounters or experiences in practice under the action of operating forces, it is less than the permissible level. That is the basically what is being targeted for. And so this basically requires that the design of the system is dynamically sound, right. So, when does that occur? The design of the system or structure is dynamically sound. And what is mean by dynamically sound design? The design is such that its characteristics, right, its modal characteristics, dynamic characteristics, they are favorable, which means that when the dynamic forces act on the system or structure, it does not unduly amplify their effect and produces a higher level of dynamic response, right. So, the dynamics of the system or structure has to be tuned in such a manner that when the dynamic forces act in practice, it does not unduly amplify their effect, right, and does not produce an output which is beyond the permissible level. So, such a design we refer as dynamically sound design, and modal analysis plays an important role in achieving this objective, achieving the objective of dynamically sound design, because modal analysis basically allows us to study the characteristics of system. So, let us try to see what are the motivations for modal analysis. Need of modal analysis. Need of experimental modal analysis, right. So, I will present two motivations, right, to understand that why experimental modal analysis is important. So, let me also write here need of modal analysis or experimental modal analysis, right. So, the first motivation is in studying the or avoiding rather the resonant operations, right. It is in the avoidance of resonant operations of machines and structures. Now, why resonant operation needs to be avoided? Why it needs to be avoided? To understand this, let me take the example of a simple system, and let us say we have a machine, right, subjected to dynamic forces, and let us represent the machine by a model of the machine, and I am using here what is called as a single degree of freedom model of the machine. So, later in the later lectures we are going to talk more about the models, right, and what is a single degree of freedom system or a model, all those things we will talk in more detail. But let us say this is a model of the machine, and the machine is represented by a mass m, stiffness k, and damping coefficient c. And let us say the machine is being acted upon by a dynamic force of of nature f naught cos omega t, right. And let us say the displacement of the machine is x in the vertical direction, and let us say it is given by x of t. And also we would see that this displacement is basically governed by omega t minus phi. So, if we analyze this system, we would come to know that the displacement is given by x of t x naught cos omega t minus phi, which means the frequency of the displacement or the vibration is same as that of the frequency of the force, and the amplitude of the displacement is x naught, and it has a phase angle phi with respect to the force, right. So, let us look at the variation of the amplitude of the displacement with the frequency of the external force, and this variation looks something like this. So, when omega is equal to 0, the amplitude of displacement is what is called as x static or static deflection, right. So, x static is equal to f naught upon k. So, when omega is 0, the frequency, the force is no longer a dynamic force, it is a static force, it is acting in the same direction, right. So, it produces a static deflection, and the k has units of Newton per meter, and hence f naught upon k gives us the static deflection. But when omega coincides or is close to the resonant frequency of the system, right, then we see a very large amplitude. So, x naught is very large, and this condition is called resonance. So, when resonance occurs, the amplitude of displacement or vibration is very large, and it would lead to higher fatigue stresses and a larger reduction in the life and larger damage it would induce, and hence resonance needs to be avoided. But the resonance can be avoided only when we know what is the natural frequency, right, then only we can avoid the resonance. So, that because if we know the excitation frequency, then if the natural frequency is known, then we would be able to figure out whether the resonance is likely to occur or not. So, therefore, to avoid resonance we must know what is resonance, and then experimental model analysis can be used, EMA can be used to identify resonant frequencies right and avoid resonant operation. So, this is one of the principal motivation for experimental model analysis. The other motivation is in troubleshooting vibration and noise problems. Let us suppose our objective is to know what is the cause of higher vibration level, right. So, we want to know what is the cause of higher vibration level. What is the cause? So, one way could be that we measure the vibration and try to analyze the vibration and see that try to figure out or determine that what could be the cause, but that could be a difficult proposition. To understand that, again let us take the system input output model, right. Right, and if the system is represented by, let us say, frequency response function alpha omega, if the input is represented by f of omega in the frequency domain and output is represented by x of omega in the frequency domain. So, these are the descriptions of the force, system and output in the frequency domain. Then we see that in the frequency domain x of omega is equal to alpha of omega into f of omega. Okay. If you multiply the input with the system characteristics defined by frequency response function, then we get the output of the system, right, in the frequency domain. And now let us say if we have higher output, which means the vibrations are higher, so you have a higher output. Now the higher output could be due to a higher input, right, that is higher f of omega, or it could be due to unfavorable frequency response function, right, or unfavorable system characteristics. Okay. So, higher output could be due to higher input or unfavorable FRF or system characteristics. So, if we have information only about the output of the system, then it would not be possible to reach to a definitive answer about whether the higher output is due to higher input or is it due to unfavorable system characteristics. So, therefore, if we can identify the system, we can analyze the system and know its the characteristics, then by analysis of the interaction between the input and the system, we can reach to a more definitive conclusion about the cause of the higher vibration levels. And once the cause is identified, then the measures to mitigate the vibrations can be planned, and the measures can be determined, right. So, this is another important motivation for experimental model analysis, right, that it will help us to troubleshoot vibration and noise problems. Therefore, today we covered the basic introduction to experimental model analysis, and we tried to answer some basic questions like what is experimental model analysis, what is the need of experimental model analysis, and some relevant background like vibrations, causes of vibration and detrimental effect. So, in the next lecture we would again further continue with little more background, right, and then we will start with the second topic of mathematical models of vibratory systems. So, thank you.